Hey, Algebra 2, how are you guys? This is Mrs. Felix, and this is Chapter 5, Section 3. We're graphing radical functions. So what we're going to learn is to graph radical functions and to write transformations. So I keep telling you guys about transformations. We're going to keep doing them, and they're always the same. So transformations of radical functions, and we're also going to graph parabolas and circles. Parabolas again, and circles for the first time since geometry, I think. So graphing radical functions. A radical function contains a radical expression. A radical with the independent variable, the x, right, in the radicand. When the radical is a square root, the function is called the square root function. When the radical is a cube root, the function is called the cube root function. And you're looking at those below. So that core concept, parent functions for square root and cube root functions. So the parent function for the family of square root functions, so there it is, f of x equals the square root of x. Hopefully you notice that it looks just like a half a parabola on its side. So the reason it's a half a parabola is, think about if we have x squared equals 4, right? So in order to solve from x, we take the square root of both sides and we get x is plus or minus 2, right? So this square root function is just the plus. It's not the minus part. If we graphed the minus part, then we would get the whole inverse of x squared of the parabola. So it's kind of just a nice thing to keep in mind. Notice the domain and the range are both only positive, and that goes back to plus or minus, right? We cannot take the square root of a negative number, so that's why the domain is only positive. And since we only included the plus part of the plus or minus, then that makes the range also only positive. So now looking at the cube root function, it looks exactly like x cubed laid on its side, right? So it's just rotated. Okay, let's look at an example. So graphing radical function. So graph each function, identify the domain and the range. So the best way to do these is just to first, think about what is the transformation that's happening. So I know that there's nothing being added or subtracted under or outside of the radical. So I know that the origin is going to be at 0, 0. And I know that there's no negative. So I know that it's going to be in the first quadrant. So to make a table for this, it's going to be fine just to start at 0 and to choose a few numbers. I'm actually trying not to look at it, but I see down here they chose 4, 8, 12, 16. And the reason for that is because they knew what that 1/4 was going to do, right? That 1/4 is going to cut our input in half or in quarters. So if we choose 1, it's going to make it 1/4. And then we're going to do the square root of 1/4, which is, it's just going to make the number super, super, super tiny. So they chose numbers that when we divide by 4, they're like still reasonable. So I think that's why they chose 0, 4, 8, and 16. And for us, this is nice too. It just makes it a little bit easier. I don't have to go back and forth with a calculator. So, well, we know that the square root of 0 is just 0, so that's nice. And then when we plug in 4, we get 4/4, which is 1, and we know the square root of 1 is just 1. So now when we plug in 8, we have 8/2, which is 2, and then we take the square root of 2, which I see down there is 1.41. So 16 divided by 4 is 4, and the square root of 4 is 2. So now we can plot these points. So we have 0, 0, and then when x is 1, 2, 3, 4, y is 1. Oops. And then when x is 4, 5, 6, 7, 8, y is like, let's say 1.5-ish. And then, so this is a really slow growing. So now we'll go, oh, they did 12 too. I skipped 12. So we're just going to go all the way to 16. This is 8, 9, 10, 11, 12, 13, 14, 15, 16. And that's finally just 2. So here's our radical function there for A. Now, they also asked us to identify the domain and the range. So the domain, x is just greater than or equal to 0, and y is also greater than or equal to 0. The domain, we should label these, and the range. Okay. So B. So for B, we're also going to want to make a table. But remember that this is the cube root function. So the domain is all real numbers. We can put in positive numbers, negative numbers. We can put in 0. So we're going to need to include some negative and some positive numbers. This negative is not going to move it up or down or right or left. So the origin is still going to be focused, or the origin is still going to be in the center. So we can still just choose some points to the right and the left. It might be nice to choose points that have a perfect cube root just so that we can have nice numbers to work with, but that's certainly not necessary. Okay, so x and y. So let's think about this. Numbers with a perfect cube root, small numbers. So obviously 1, and then 2 times 2 times 2 is 8, and then 27. So if you want to choose numbers with perfect cube roots, just to make the math easy, so you don't have to use a calculator, you can do -27, -8, -1, 0, 1, 8, and 27. Okay, so let's start with the easiest one. Let's start with 0. The cube root of 0 is 0. 0 times anything is 0. So we knew that would happen, though. We knew that since there was no h or k, right? We weren't moving right or left or up or down. We knew that the center was going to be at the origin. So now 1, the cube root of 1, positive 1, let's do positive 1. The cube root of positive 1 is 1, because 1 times 1 times 1 is 1. So 1 times -3 is -3. So now on the left, if we do -1, the cube root of -1 is -1. And then -1 times -3 is +3. Okay, let's do 8. We know that the cube root of 8 is 2. 2 times -3 is -6. So we know this is going to have symmetry, so we don't even have to think about -8. We know it's going to be +6. 27, the cube root of 27 is 3. 3 times -3 is -9. So we know over here we're going to have +9. So now we can graph. Let's see. So we have kind of need a little bit more for the domain here because I have to get all the way up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, barely. 2, 3, 4, 5, 6, 7, 8, 9. Now, in the x direction, I'm going to count by 3s just to make my life a little bit easier right now. So 3, 6, 9, 12, 15, 18, 21, 24, 27. So let's just show what we did there. 12, 15, 18, 21, 24, 27. Okay, and we'll do the same thing over here, but I'm not going to label it. It needs to be a little longer too, huh? Okay, 3, 6, 9, 12, 15, 18, 21, 27. Okay, here we go. So we have the origin. And then when we plug in 1, okay, let's see. I have 1. Let's say it's right about here. And then I go up or down to -3. So 1, 2, 3. All right. And then on the negative side, I have -1 and +3. And now I have 8, which is right about here. And then I have -6. So this is 3, 4, 5, 6. Should have counted by threes going down too, because these are all going to be multiples of 3. This is 3, 4, 5, 6, 7, 8, 9, just to make it easier. 3, 4, 5, 6, 7, 8, 9. There we go. Okay, so over here, I'm going to have 3, 6, 8, and +6. And now I'm going to have, so 27, +27 is -9, which is right about here. And then -27 is +9. So there we go. So now this isn't a line, right? Remember, I have to connect this with a smooth curve. I know how this is growing because I know what the parent function looks like. So something like that. There we go. And now we have to identify the domain and the range. So the domain and the range are both all real numbers. Domain and the range are, however you want to write that, we can just use words. All real numbers. Or you can say y exists in, you can say, it's easy enough just to say y exists in the real numbers too. Okay, cool, cool, cool. So let's check our work here. Domain and range are all real numbers. Cool, yep, we did great. Good work, you guys. Example, there's so many examples in this section, I think too. So bear with me, you might need to take some breaks. I hope this does not look overwhelming to you because this is exactly the same chart we have gotten every time we've learned a new function. Take a good look at it. Nothing has changed. When we subtract from the x, we go right or left. When we add to the function, right, the whole function, we go up or down. When we have a negative with the x's, we flip the y-axis, right? We flip over the y-axis. If we have a point over here, and we change the x to a negative, it's going to flip over here. If we change the y to a negative, it's going to flip down, right? Stretches or shrinks, so this is the same. If you multiply the inputs, it's a horizontal shrink by a factor of 1/3. If you multiply the inputs by a fraction, it's a horizontal stretch. If you vertical stretches and shrinks on the outside, right? If it's a whole number, it's a vertical stretch. If it's a fraction, it's a vertical shrink. So maybe print this out, hang it on your wall, or take good notes, make flashcards, and just get used to this stuff. This is always, always, always going to be the same for every single function. Every function works the same way. Okay, so transforming radical functions. Describe the transformation. So describe the transformation and then graph. Okay, so this -3 on the inside, remember this is going to be right 3, and then the 4 is up 4. Okay, so this is just there's no stretch or shrink. So this is just our parent square root function. So if we have 0, 1, 2, well, wait, let's do 0, 1, 4, 9. So the square root of 0 is 0. The square root of 1 is 1, 2, 3, right? It's just our parent. Do we have to graph each? Yeah, we do have to graph each. So we'll graph our parent square root function. So 0, 0, and then 1, 1, and then 1, 2, 3, 4, 2. It's just like a sideways parabola, right? 4, 5, 6, 7, 8, 9, and 3. So here's the parent function. Now, when we do the transformation, so we can change colors too. So the transformation is going to look exactly the same. It's going to have the same exact shape and size, except it moves right 3. So 1, 2, 3, and up 4. So this is 3. So here will be 4. And now it's going to look exactly the same. So if we look at the origin here, we went up 1 and over 1. So we can just do that, up 1 and over 1. And then from that point, we went up 1 and over 1, 2, 3. So we can go from this point, we can go up 1 and over 1, 2, 3. And now from this point, we went up 1 and over 1, 2, 3. Is that 5, 4, 5? Yeah, between 4 and 9. Yeah. Okay, so we go up 1 and over, let's say 1, 2, 3, 4, 5. This would be so much easier using graph paper. So that is using the transformation. So we used what we know about transformations just to copy the green line up to the blue line. Now, you do not have to do that way. You do not have to do it that way. You can also make a table. And this time we know we're going to start at, let's see, it moved right 3. So we're going to start at 3. But the problem now is we have to find, oh wait, yeah, the x is 3, right? Right 3, yeah, right 3. So we have to now plug 3 in. So 3 minus 3 is 0, plus 4 is 4. So let's see. The next point we can do is when we just add 1. So we'll do, that way it'll give us, I'm trying to think about how we can take nice square roots. So if we have 4 for x, then that's going to give us the 1, right? So if we put in 4, we get the square root of 1, which is 1 plus 4 is 5. So that gives us this point here. Now we have these 2 points. So now I still want to do nice square roots. So let's see. What minus 3 gives us 4? So 7. 7 minus 3 gives us 4. The square root of 4 is 2. 2 plus 4 is 6, right? So now we're just doing the move up 1, move up 1, move up 1. Okay, so what should be our next x? So I did the square root of 4, so now we want to do the square root of 9 because we're trying to do perfect square roots. So what minus 3 is 9? 12. So then we get 3 plus 4, which is 7. 4, 5, 6, 7. Beautiful. Okay, so you can make a t-table, but look at how we ended up doing exactly the same thing. Okay, so that was A. What else? Do we need to talk about the domain and the range or anything? Well, I think we should. Do they do it eventually? So the domain for the green one is still just positive and negative, right? The domain is x greater than or equal to 0. The range is y greater than or equal to 0. But the blue one is different because the blue one's not at the origin. So the domain for the transformed function, our x's start at 3. So x is greater than or equal to 3. And you can look inside here too. What makes x minus 3 equal to 0? So this is your question. Not 0. Well, equal to 0. Yeah, that's the smallest it can be, right? We can't be less than 0 under a square root. Now the range, let's see, where does the range start? 4. So the range, it's always limited by the vertex. So y is greater than or equal to 4. All right, so now let's do B. That new problem is getting in the way here. Okay, B. All right, so our parent cube root, I wonder what the best way to do this one is going to be. Maybe we're just going to make a table. Okay, well, let's just start by making a t-table for our parent cube root function. So we know that we can have negatives and positives. We can use perfect cube roots. So we can do, well, we can just even do, let's see, I guess I don't want to always have to do 27. What does your book do? Do they just do 8? Yeah, they just do 1 and 4. Okay, so we can do -8, -1 and 0, 8 and 1. And then the y here is going to be -2, -1, 0. Oh, I put these backwards. 1 and 8, 1 and 2. So that's our parent cubic. So now our transformed cubic. I'm trying to think of how to get nice numbers in there, but I don't really think I can. So it's still centered right around the origin too. So I guess we'll just do the same numbers, -8, -1, 0, 1 and 8. But now we're gonna have to just do the math for it. I have a calculator here. Wait, let me grab it. The TI, what is this? 84. So I'm just gonna type in, if you hit the math button and you have a graphing calculator, if you hit math, it's the 4th option on the column that's already open, the math column. That's the cube root option. So then you can just type in, well, we're going to have -8 times -8. So there's 2 negatives. So we don't really care about the negatives. So that just ends up being 4. Really cool. Let's see. I get kind of paranoid with these calculators. Sometimes for me, it's helpful to use like just parentheses, always just parenthesis, but that's 4. So now if we do 1, we're going to end up with 8. So +8. So this is going to be +2, right? Now 0 times 0 is 0. The cube root of 0 is 0. 1 times -8 is -8. Oh, I'm so glad we ended up with nice numbers. This is cool. 1 times -8 is -8. So this is going to be -2. And then this is going to be -4. We know we're going to have this symmetry. So cool. So this is great. This is nice to graph. Let's see. Our x has to go to 8 and -8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I think I made the negative ones a little bigger, but that's okay. And then the y, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so when x is 0, y is 0. I'm doing the parent function first. I'm doing this one first. When x is positive 1, y is 1. When x is negative 1, y is negative 1. When x is 8, so this goes all the way out to 8, y is 2. And then when x is positive 8, y is, or negative 8, y is negative 2. All right. Here's our parent function. It would have been nice had I gone through all the lines. Okay, so now for our transformed function. So let's just see how the y's, how this is like stretching. So instead of 1, we have 2. Instead of 4, we have, or instead of 2, we have 4. And also that, notice that the negatives have switched. So this is going to be a reflection. All right, so we still have 0, 0. And then when x is 1, y is 2. Negative 2. When x is 8, y is negative 4. Okay, and now we have the reflection of that. So when x is negative 1, y is positive 2. And when x is negative 8, y is positive 4. All right, so this is actually kind of hard to see how it transformed. I'm sorry, I just drew that so badly. Since I drew this so poorly, I'm going to take it over to Desmos. Let's open a Desmos. All right, so the parent function is just a cube root function. Oh, wait. Functions, let's see. Why don't they have it easier? Okay, we can do that one. Cube root of x, and then we had the cube root of negative 8x. Okay, there, now you can see it. So since the multiple, the scalar, the 8, is inside with the x, so being multiplied by the x, then remember x is the horizontal axis. So since it's further away from the x, then and it's like, let's think, how's the way to explain this? Since it's a horizontal shrink, because if you think about the red one, right, the parent function, and if you imagine putting your hands on both ends of it, you would have to smash it from the ends to get the blue ones, right? So since the blue function is smashing the red one horizontally, then it's a horizontal shrink. Since it's a shrink, we have to say by a factor of 1/8, which is mind-blowing, right? Because it's an 8. But since it's a shrink, then it's a fraction, right? Because fractions shrink things. Like, would you rather have an 1/8 of a pie, right? That's a fraction of a pie. So you're shrinking your piece of pie if you cut it, right? I'm hoping to help you make sense of that, but I don't know if I'm getting more confusing by now talking about pie. So also we have the negative in front. And since the negative is inside with the x, then we're reflecting the y-axis, right? Think about what we talked about before. If you have a point in the first quadrant and you change the sign of the x, then it's going to flip it over to the second quadrant. So we're going over the y-axis. So we say it's a reflection in the y-axis, even though the negative is to the x. Okay, I hope that was more helpful than my drawing. Yes, definitely more helpful. Those look exactly the same. All right, and that is it. Here's the solutions, but also you can be following along in your book. This is on page 253. Okay, let's see. That was example 2. Where's example 3? Did I skip example 3? Whoops, did I hate example 3? What's happening here? Let me look in your book. Oh, I skipped it because that's modeling, and I don't like confusing you with modeling problems during these lessons. So and I try not to give you modeling homework unless I think it's really interesting and useful. But usually your book tries too hard, and I don't think you need to be thinking about items dropped on Mars right now. All right, let's just do the math. So example 4, writing a transformed radical function. So they're going to tell you what to do to the parent function, and then we have to write the function that does that. So try to ignore the solution, and let's just read the problem. Let the graph of G be a horizontal shrink. So that's what we just did over here, right? This was a horizontal shrink by a factor of 1/8. So they say a horizontal shrink by a factor of 1/6. So if we do that right away, let's just do one step at a time. So we're doing it to the cube root function. So if f of x is the cube root of x, then a horizontal shrink by a factor of 1/6 is going to be that. Right? It's going to be 6, not 1/6, because it's a horizontal shrink. Okay. And then follow that. So the next step is a translation 3 units left. So that is going to go inside. So now we're going to have f of the next thing we're going to do. You know what? Maybe we should now call this. So let's call this one. Let's call this one h of x since we're not done, and they want our final one to be g of x. So we'll call the next step h of x. So to h of x, we're going to go left. So we're going to add 3 on the inside. Oh, it's going to look like add 3. Do you guys remember that though? But really we're doing negative 3. Okay. So now we're going to take h of x, which is this step here. So we have the cube root of, oh, I still wrote 1/6, even though it was a 6. I'm so sorry, you guys. I said that here, but then when I wrote it inside, I wrote it as 1/6, and that was probably really confusing. Okay. So now we're going to add 3 on the inside. So we have 6. So to the x, we're going to add 3. So now we simplify that. And we get 6x plus 18, and we call that g of x. So one step at a time, right? Just do it when they say followed by, you have to do it one step at a time. So that's the super confusing thing. If it's just like bullets, like change this and this and this and this, then you can just like plug them all in. But when they say followed by, you have to do the first one and then you have to transform the second one. All right. Okay, graphing parabolas and circles. If you need to take a break and you haven't already taken a break, this is probably a great time to take a break. We're also done after example 6. So we're going to graph a parabola, and then we're going to graph a circle, and then we're all done. Sorry, this is such a long section. So to graph parabolas and circles using a graphing calculator, first you have to solve their equations for y. Okay, so you only have to do that if you're using a graphing calculator, like an actual Texas Instruments graphing calculator. But luckily for you guys, your class is now on a computer, so you can just use Desmos. You can also download the free Desmos app on your phone, and you never have to worry about buying a $100 graphing calculator. Or solving for y, right? If you had to graph it into your calculator, they're right. You cannot type this into your calculator. You have to solve it for y and then write the positive and the negative so that you get the plus part, which is what we were talking about earlier. So that's the plus part and the negative part. So it gives you that whole parabola on its side, which by the way, isn't a function. But we should be able to plug it straight in Desmos, I'm pretty sure. So let's go try. It's 1/2 y squared equals x. Okay, let's see what happens. I hope I'm right about this. I think Desmos is smarter than our graphing calculators. It should be, right? 1/2 y squared equals x. Bam! Yes, no solving required. Take that. Okay, so pretty cool, right? And now the circle, it tells you the same thing for the circle. So let's go back to our notes. Example 6, graphing a circle. So I want you to know when you look at this that this is a circle. So you should know that this format here is a circle. X squared plus y squared equals r squared. X squared plus y squared equals r squared. So the square root of this number is the square root of, let's say n is r, right? So the radius of this circle here is 4. And then the center of the circle, so the center is at, oh shoot, you guys. I have to do a little thinking about this. I think it's just positive HK. So in this case, it's 0, 0 because there's nothing being added to the X or the Y. But let me just take this over to Desmos and be sure about that. Okay, so X squared plus Y squared, that was their circle. X, but you know what? Let me just show you. So X, I'm not totally sure. X plus H squared y minus, I can't remember if it's a plus or a minus. And instead of like Googling it and looking it up, equals r squared. So this is the standard form of a circle. Well, x squared plus y squared equals r squared is a standard form of a circle. But then when we put in the h and k's, we move it up and down, right? So if we put in all of these sliders, now, okay, yeah. So this is the right circle. So see how the center of the circle is at 1, 1. That's because the sliders are all set to 1. And the radius of the circle is 1, and that's because that slider is set to 1. So if we move the h and the k to 0, it's now centered at the origin, right? So yes, I was right. Yay, without looking it up. The center is at HK. So the standard form of a transformed circle is X minus, I might have the H and K backwards too, but it doesn't matter. Y minus K squared equals R squared. Okay, and you would have to solve for plus and minus Y if you were to graph it using a graphing calculator, but you can just plug it into Desmos and make sliders and do awesome things because Desmos is awesome. So, and now you know how to move a circle and you know how to make it bigger. It doesn't matter if it's negative because you're squaring it. So fun, huh? Okay, and now that's our last example. So you guys are good. Thanks for all your hard work. I'm so proud of your effort. I appreciate everything. Come to class with your questions. I look forward to working through challenging problems with you.